This is part 6 of the module 11 lecture. In this part, we're going to learn to test a hypothesis about the slope parameter. And this corresponds to section 13.3 in your textbook. All right, so in here, we're going to use the least squares estimates, A and B, that we calculated. And we're going to use those to make an inference about the parameters A and B. The main idea is that we want to see if these parameters are non-zero. So as we saw when we interpret the slope in the previous lecture or in the previous recording, we know that the parameter B determines the magnitude of how much the response variable changes per each unit in the variable x. So if this parameter is actually equal to 0, B, or in other words, if the actual slope is equal to 0, then we know that the variable x has no effect on the response variable. Now, if we look at the magnitude of the parameter A, that simply tells us where the line intersects the vertical axis. And that is when x is equal to 0. So when x is equal to 0, A tells us the average of the response variable y. But it doesn't tell us anything about whether x affects y. So the key inference here is to determine if the slope parameter is 0 or not. Because if it is 0, then we know that y does not depend on x. If it is non-zero, then we can use that parameter to determine how much the response variable is going to change per each unit of the independent variable x. All right, so the inference of interest in regression analysis is determining if the slope is non-zero. So for that reason, to do this inference, we perform a hypothesis test, where the null hypothesis is that the slope is 0, meaning x does not affect the response variable y. And the alternative hypothesis is that b is not 0. And again, it could be negative or could be positive. So in this particular test for the slope is a two-tail test. Because in the alternative hypothesis, we want to find out if the slope is not 0. And I added these figures to give you an idea of what we're doing when, for example, we do not reject the hypothesis, or rather when we fail to reject the hypothesis that the slope is 0. That means that the line is parallel to the x-axis, meaning y does not depend on x. Or we could have a situation where we're trying to fit the straight line model to something that is not straight. And this curve is balanced so that the fitted line is just horizontal to the x-axis. So if we decide that the parameter is equal to 0, the slope parameter is equal to 0, that means the line is parallel to the x-axis. If we reject the null hypothesis, we say that the slope is not 0, then we may have a case where we have a positive relationship between x and y, or we may have a negative relationship, or we still have a linear relationship, but maybe the model is not correct for the data that we have. So, but here are the consequences of failing to reject or rejecting the hypothesis that the slope parameter is 0. All right, so how we perform this hypothesis? Well, we need to look at the sampling distribution of the least squares estimate of the slope, B. So in this case, as long as the random errors are independent, and the mean of the sampling distribution of B then is mu sub B, and the standard deviation is given by this expression, which is the variance of the errors divided by the sum of squares of that x, the square root of that. Now, the random errors are assumed to follow a normal distribution. Therefore, we can say that the sampling distribution of B is also normal. And notice that here we're assuming that we know the variance of the random errors, that we do not. So if we replace that by the standard deviation of the residuals, then you know that we're going to be using the t distribution, because a population standard deviation is replaced with the sample standard deviation. All right, for this test, the test statistic is defined as this, as a difference of the estimate minus the proposed value for the slope, b, and because under the null hypothesis b is 0, this b disappears from the numerator, and so this test statistic simplifies to this. And all I did here is this square root of the sum of squares of the xx. I just moved it to the top part of the division. So now it looks like this. But this is the definition of the test statistic under the assumption that the slope is 0. All right, so now this is the form of the test statistic that we're going to use. Now we determine that the sampling distribution is normal, and as I mentioned earlier, the variance of b is unknown, so we're going to replace it with its estimate, so using the standard deviation of the residuals. And because we're doing that, and because the sampling distribution of b is normal, then we're going to use the t distribution to conduct this test. And it'll be a t distribution with n-2 degrees of freedom. All right, now that we know that, then we follow the same approach as before. So if we decide to use the critical value approach, then we know that this is a two-tail test. So we're gonna have two rejection regions, one on the left, one on the right. And then also we know that to find the critical value for the upper region, we find that in table 5 using alpha over 2 and the degrees of freedom of n-2. That will give us this upper critical value. To find the lower critical value, we use the symmetry of the t distribution, and we know that it's just a negative value of the positive value that we found. So if the value of the test statistic lies in either rejection region, then we will reject the null hypothesis. Now, if we decide to use the p-value approach, again, this is a two-tail test. So what we do is we take the upper t-value and we find the probability for that, for the t observed, and multiply by 2 to obtain the p-value. So here's a formula that will give us the p-value. And again, we're going to use table 5 to guess, or not to guess, but to find bounds for the p-value. If we want to find the exact p-value, we can use Excel with this formula and find the exact p-value. And the same rule that we have been using since module 8 continues to apply. That is, if the p-value is less than alpha, we reject the null hypothesis. All right, so in the next recording, we're going to solve an example and see how we do a hypothesis test for the slope parameter.